Okay, we're going to do a quick review about geometric probability. So some of the vocabulary. An event is let's try that again. An event is a desired outcome. So something you want to have happened or a set of outcomes. The probability of an event is from 0 to 1, 0 being impossible, 1 being certain. Okay, that's the measure of likeliness. Likelihood. I don't think that's how you spell that, but anyway. So your fraction or a decimal or a percent, it's going to be what you want to have happen over all the things that could happen. So, for example, if you have 500 samples of monitors, 3 of them are defective. Probability of one being defective is 3 out of 500. Okay, a jar contains 10 red marbles, 8 green marbles, blah, 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 blah. All right, so we want not green. So first of all, the total is 10, 8, 11. 10, 8, 5, and 6 makes 11, so it's 29. Okay, so that's our denominator. Now let's count up how many are not green. So it's going to be 10, 5, and 6. So it's 21. Out of 29 would be the probability of not green. Okay, and then when we get to geometric probability, we're talking about the probability that if random, you would pick a point that was in the triangle N. So the probability of picking a point in N randomly would be the area of N, which is the desired, that's what you want, over R, which is the total area. So that's going to look like a fly landing on the diagram, finding the probability that it will land on the red. So what we want is the area of the red is going to be 3 times 3.5. And I just put a 4 and it's a 5. 3.5. So 3 times 3.5 is going to be 10.5. So the probability of red, the numerator is going to be 10.5. The denominator is going to be, we could just add up the sides. So this is going to be 6. This is 6. So it's a square. It's a 6 by 6 square. So the area of the whole thing is going to be 36. So the probability of red is 10.5 over 36. I don't love decimals in there, but we're just going to leave it like that. So the probability of not red is going to be 36 minus 10.5. Whatever the difference is, whatever's left, is going to be the probability of not red. So $25.5 makes sense. So the probability of it not landing on red is 25.5 over 36, which, if you added them together, would be 36 over 36 would be the probability it landed somewhere in the square would be 100%, because we're going to assume it would land somewhere in that square. Okay, so there's 2 different things that we talk about when we're talking about probability. Sometimes you see the word and sometimes you see the word or. So if you see the word and, you're talking about more than one thing happening. And what you need to do is you need to find the 2 separate probabilities and then multiply them together. So if you're flipping a coin and rolling a dice, you would say the probability of getting heads is 1 out of 2. The probability of rolling a 2 would be there's 1 2 out of 6 sides of the dice. So if now if you want the probability of flipping a coin and getting heads and rolling the dice and getting a 2, so I want both of those things to happen, I'm going to multiply that together. 1/2 times 1/6 is 1/12. And it kind of makes sense if you think about it, because you have a 50-50 chance of getting heads, a harder chance of getting a 2 on a dice. So if you put those together, it should be even less probability, more difficult. Anyway, you get it. Okay. When you have or, you're talking about one thing happening, but there's more than one thing that could happen. So you're adding the options in the numerator, and the total's going to stay the same. So for example, if you're rolling a dice and you want to get a 5 or a 6, then you have the probability of getting a 5, the probability of getting a 6, and then you're going to add those together. The probability of getting a 5 or a 6 would be 2 out of 6, which is 1/3. So it should be more likely that you're going to get what you want, because you're saying that if you get more things, that would satisfy your event. Okay. All right, so let's do a couple of these problems. So same thing over here. So we're going to want the probability of getting a head and getting a 6. So this is going to be just like the one we just did in our example. Here's our word and. So, and you notice we use P for probability, and then in the parentheses we put what we want to have happen. So getting heads is going to be 1 out of 2. The probability of rolling a 6 is going to be 1 out of 6. So the probability of heads and a 6 is 1 out of 12, because we multiplied them together. And then you could also turn that into a decimal or a percent if you remembered what 1 divided by 12 is, because you would just divide it. So you would get 0.083 or 8.3%. Not a very good chance of getting a heads and rolling a 6. Okay. So here's one where we have an or. So this one we should have a more likely chance. So first of all, our total amount of candy is 12. So the probability of red or blue, I wasn't going to use the big B, but let's just use a little b. Okay, that's going to be, red is 6 out of 12. Blue is 2 out of 12. So the probability of getting red or blue is going to be 8 out of 12. And we can simplify that to 4 out of 6 or 2 out of 3. So this would be the best answer because it's simplified. But notice we're adding together. Or means add, and means multiply. Okay. So then there's this other thing we have. We're picking, so we got an and notice we put it back. So the total amount of candy in the bag stays the same, because otherwise we change our denominator. So the probability of picking red is going to be 6 out of 12. The probability of picking blue is going to be 2 out of 12. So if I want the probability of picking a red and then picking a blue, I'm going to multiply those together. So I'm going to have 12 out of 1 44, which is going to be 1 out of 12. So there's 8 red and blue, right? But if we want each one to happen, then we have 8 out of 144. 12 out of 144, which is 1/12, which is way smaller than 2/3. Okay. The other thing that we need to talk about is combinations and permutations. And these get a little complicated, so we're going to see if I can do these without confusing myself. All right, combinations mean order doesn't matter, which doesn't seem like, to me it seems backwards, okay? But because if order doesn't matter, there's less options. Because if you have something that happens, if you have 2 things that you want to happen, it doesn't matter if the first and second thing happen or if the second and first thing happen, they count as the same combination. So that's doubling up so you don't count both of those. So if you have 3 cookies and you eat 2, you can eat the first one and the second one, the first one and the third one, or the second one and the third one, okay? So a lot of times those are options for choosing things like what order. Permutations, order does matter. And so there's more options, which seems backwards, but there you go. So combinations, we had kind of the same amount of options, but we had to get rid of some of them because it didn't matter if they were in reverse order. So we had to take out the ones that were just reversed. If you're doing permutations, since it does matter, now we have 1, 2, 3, 4, 5, 6. So we had 6 options over here. Oh, nope, we had 3 options over here. Whereas we have 6 options over here because the order that it happens matters. So this would be something like arranging people or numbers or picking a president and a vice president or something like that. So the next 2 problems, see if this makes sense. If I have 4 friends, so this one is going to be our combination. Because first of all, co-president, so it doesn't matter like which one's first and which one's second because they're both going to be president. Okay, so how many groups of 2? So I'm going to put J, E, B, N, A. So all the combinations are going to be, I guess I'm just going to make a list. Okay. Joseph and Elia, Joseph and Brianna, Joseph and Alex. So when I do Elia, I'm not going to do Joseph because we already have that one. So I have Elia and Brianna, or Elia and Alex. And then when I do Brianna, I already did Brianna and Joseph. I already did Brianna and Elia. So I can do Brianna and Alex. And so that's it. That's all the possible combinations of co-presidents. Because if I switch the order, they would count as the same thing I already listed. So I have 1, 2, 3, 4, 5, 6 possible combinations. Okay, so, and then I tried to make this one a little bit different, which is going to be permutations. Because order matters, I have the one person president and one person vice president. So if I have Joseph and Elia, I'm assuming he's president, she's vice president. I also have to have Elia and Joseph, because now she's president, he's vice president. So I have Joseph and Brianna, Joseph and Alex. So all those have Joseph as the president. If Elia is the president, then there's 3 possible ways they can do president, vice president. If Brianna's president, we have those. And if Alex is president, We have those. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now we have 12 possible combinations. Because it matters the order. So it seems like having the order mattering should make less combinations, but really gives you more combinations. Because if the order doesn't matter, you have to take out some of the combinations because they're repeating. So hopefully that makes sense of probability.